Welcome to this series of video lectures introducing system engineering. I am Bob Parkinson and I'm a visiting professor at Cranfield University.
And I'm Mark Hempsell of Bristol University. Bob and I are all colleagues. We used to work together on systems engineering in the space industry, and we have both taught systems engineering at university level.
During our time in the space industry, we have between us worked on many projects, such as the space platform, which was originally a contribution to the International Space Station and then evolved into ENVISAT, both the HOTOL and Skylon spaceplanes, satellites like Inmarsat 2, the DCX Delta Clipper launch system proposal, the Bepi-Colombo interplanetary probe to Mercury, and most recently the Scorpion nuclear space transport system.
Although Bob and I's working experiences with satellites and launch systems, systems engineering is not just something used by the space industry. It actually came out of the aircraft and computing industries and is now used by all engineering disciplines when dealing with large complex projects. So, what is systems engineering?
Well, Mark, before I can answer that question, we first need to understand what a system is. There are many different dictionary definitions that emphasise that it is a set or collection of components that interact in a way for a common purpose.
The original word is Latin, and it meant things that work together in harmony, like two musical notes or the planets in the heavenly sphere, hence solar system. So you can find uses of the word system that mean something a little different than that, but hold back to the original Latin root.
For our purposes, though, we need something a little more precise and focused. So let's try this. A system is a set whose elements interact with each other to create emergent properties. Now we must unpack this definition and explore its implications, starting with what we mean by a set.
Well, a set is a collection of elements that's defined by a boundary, and that boundary is defined by words. Element is just the word we use for something that's in a set. It can be anything. In maths it can be numbers, in law it could be collections of legislation, and in other contexts it can be actual physical things. Here we have a set. It is the set of guitars owned by me, Mark Hempsell. Although these are physical objects, they are only guitars because we humans have a concept of what a guitar is. But should the bass guitar be included? Most dictionary definitions of a guitar emphasise 6 strings, so even this apparently simple concept has blurred edges, and that would need clarifying for a precise definition. Also note that in part this set is defined by the legal concept of ownership, which has nothing to do with the way physical matter is arranged in the real universe. Here is another set. It's the set of guitar amplifiers owned by Mark Hempsell. But neither of these two sets are systems, as neither the guitars nor the amplifiers interact with each other. In fact, apart from the acoustic guitar, none of them do anything at all. What makes a system different from other types of set is that in a system these elements are connected to each other. We call these connections interfaces, and through these interactions they do things together that they cannot do alone. This is the emergent properties. This is the system model, which is just the definition we have already seen in a pictorial form. This is an abstract conception which is the basis of all systems thinking. Now, we've got to issue a warning here. The system model means the abstract notion of a system. Later in the course, we were discussing models of systems that we shall also be calling system models. Indeed, we shall have a whole lecture on them. Right, okay, this is a bit confusing, we know, but it's the terminology used in the real world, so stay alert when this term is used, as it could have any one of the two meanings. Now let us turn to the concept of emergent properties. It is what makes a set a system, but it is sometimes difficult to grasp, so let's look at it in action. Here I have an acoustic guitar, and in the right hand it can make music. Well, okay, these might not be the right hands, but you get the point. Here I have an electric guitar, and by itself it cannot make effective music. But here I have an amplifier. Again, by itself it cannot do anything except maybe be an expensive doorstop. And here we have some loudspeakers. Again, by themselves they do nothing. But if we consider them as elements of a system and they are correctly connected together using the internal interface of a 1/4 inch jack and the power interface of a 3-pin plug, then together we have a system that can now make music. Well, depending on what you call music. The ability to make, well, let us call it sounds, is the emergent property of this system. The emergent properties are important because it is intended emergent properties that we are after. They are why we go to the trouble to build the system. You'll notice I emphasised intended. It is often forgotten that a system could also have unintended emergent properties. So while it is important in system design to ensure that the desired properties are achieved, it's just as important to ensure that the unintended emergent properties are also understood and adverse consequences controlled. Okay, you may be saying, got that, but surely the same thing can be said for the acoustic guitar. The strings by themselves do nothing, the fretboard does nothing, the body does nothing by itself. It's only when they're connected together that they become a guitar. So is the acoustic guitar a system? To take this line of argument further, I heard a story that when a senior member of the UK's Defence Research Agency heard the definition of a system for the first time, he said, well, that's meaningless. It could be applied to a pair of boots. So is a pair of boots a system?
Well, the answer in both cases is yes, if you want them to be. The system model can be applied to many things, but why should you bother? If you can understand the object without treating it as a system, then you wouldn't. What makes a system is not any property it has in the real world, but that it is something that we need to impose on the system because it's too complex to understand otherwise. A system is something we choose to call a system. Mark's electric guitar setup is complex, and I doubt if Mark understands it all in detail. So he will be treating it as a system, buying the major elements which are in themselves complex, and then connecting them together without understanding their detail. But he will not be consciously using the system model or using system engineering when putting it together. So we'll call the creation of systems on this scale small projects. Things that we either subconsciously or informally treat as a system, but that are not formally, we don't informally impose the system model on them. We do not need to use system engineering as the system can be managed in one person's head. Unfortunately, many of the things that we do nowadays are too big to be managed in just one person's head. They will involve specialists in different disciplines who will use different technical language. They will belong to different companies and may well be located in different countries where they will not even speak the same native language. We're now in the realm of large projects, and to understand them we need to look at the history of engineering projects.
One of the most common aspects of being human that is often used to distinguish us from other animals is the ability to make tools. In other words, engineering. And the archaeological record shows that even pre-humans were making things single-handedly by themselves either for themselves or for the wider community. To do this, the individual has to have both an understanding of the item being made and the time available to make it. At some time, mankind learned to work together, to organise themselves to share labour in order to make things that no one person would have the time to make. Things like the pyramids. Everyone can understand it. After all, it's just a pile of stones. But no one person could build it. Or medieval sailing ships. Again, everyone making it could understand how it worked, but it's way too big for one person to make. Or aircraft like the Spitfire. As these examples show, engineering has progressed to increasingly complex things, but although they require large teams to split the work effort, everyone on the team could understand the whole. The Spitfire is an interesting example. Here's a quote from its designer, R.J. Mitchell. "If anyone ever tells you anything about an aircraft which is so bloody complicated you can't understand it, take it from me, it's all bollocks." Well, Mitchell had a reputation for earthy language. But the point here is that he expected everyone on the team, in this case it was the test pilot, to understand how the aircraft worked. And at that stage of aviation technology, I think he's right. But I also think that aircraft that entered World War II, like the Spitfire, are on the limit of this process. If you had a degree in aeronautical engineering, then you'd been trained to understand everything about an aircraft as sophisticated as the Spitfire. But the pressure of war on technical developments changed that. As Rear Admiral Grace Hopper puts it, life was simple before World War II. After that, we had systems. And there were two areas of technology in particular where this problem revealed itself. One was aviation. For example, the Boeing B-29 Superfortress. This had a massive development effort. It actually cost 50% more than the Manhattan atom bomb project. And of course, the B-29 was later used to drop the atom bomb. This aircraft had computer-controlled gun turrets, cabin pressurization, friend-foe identification, radio navigation, blind landing systems, indeed an entire complex suite of what we would now call avionics. In short, it was way past one person's ability to fully understand how it worked. The other area that faced this problem was electronic computing, a field that was born during the war, and indeed the term systems engineering seems to have been first used in the 1940s at Bell Laboratories in the context of computing.
So, during the Second World War, things had got too complex for one person to understand everything. Humanity had reached what we're going to call the complexity barrier, and system engineering is the way we broke through it. So large projects involve creating things so complex that a single person cannot keep up an up-to-date full understanding of the design information and the project status. This means using system engineering methods and tools, things we call a system model, that ensure that everyone on the team has a common understanding of what the system is and up-to-date access to data giving the current state of the design, even while that design is evolving and changing. The key way this understanding is distributed is the use of specifications, which are formal definitions of the system and all its components. These specifications can define requirements, designs and procedures. We will be looking in particular at the system requirement specification in the next video. The most common problems in large projects are due to failures in communication between the people involved in the project. So a lot of real-world system engineering practice is targeted at minimising these failures. But before turning to system engineering, we need to have a philosophical understanding of just what engineering is.
There is a point we need to make here. You can also use the system models in science. However, there is a subtle but important philosophical difference between using system models in science and using them in engineering. Here we have a bird, specifically a red kite, clearly as complex as any man-made aircraft, and we could use systems modellings and approaches to gain an insight into how it achieves such elegant flight. But is the red kite a better bird than, say, a robin or a swan, or indeed any other bird? Well, we might say that the robin is cuter, or that the swan is more elegant, but these are just projecting our personal aesthetics onto these birds. We cannot make objective statements about their relative merits because they are just natural objects that simply exist and have no purpose. Now let's look at how this video was taken. It was taken from this drone, which can not only do some spectacular flying of its own, but also at the same time it can track objects automatically to video them. So this is also clearly a complex system. But can we objectively say that this drone is better than another drone? Well, yes, because it has been built with a defined purpose and we can judge it against that purpose. This is a process known as validation. This is the difference between science and engineering. Science explores the universe we find ourselves in with the goal of trying to understand it. Engineering changes that universe to meet purposes that are defined by humans. So systems engineering is the application of the systems model to the engineering of complex objects that humans create to fulfill a purpose. The concept of purpose is important, and it is at the heart of all engineering, and we will be returning to it in the next video.
So, now we understand what engineering is, we can understand that system engineering is just the engineering of systems. Just as structure engineering is engineering with structures, and electronic engineering is engineering which uses electronics. So let's look at some definitions of system engineering. This definition is from the International Council on System Engineering, normally called INCOSE, which is the leading academic body promoting system engineering. But to be a little critical, this more describes what it's supposed to do rather than what actually happens. This is another definition, this time from the European Committee on Space Standards, an organisation of European space agencies and companies. This definition is full of jargon, which by the end of the course you should understand, but at the moment confuses. Again, to be a little critical, it is more an explanation of how it works rather than what is. This definition is from an old textbook called System Engineering and Analysis by Aslaksen and Weicher. It highlights problems with academic consideration of the subject by suggesting that once the requirement specifications are in place, system engineers can leave the project. As you'll find in these videos, real-life system engineers are active throughout the product delivery, and in practice, most of the system engineering happens after the requirements have been agreed and the project is in progress. The message here is to be careful of definitions of system engineering. For our videos, we'll use a broader definition of system engineering as simply the creation and maintenance of systems to meet defined objectives.
Well, now that we've defined systems and system engineering, and we've introduced the concept of emergent properties and the complexity barrier, I think there's one more aspect of the generic system model that we do need to consider.
Well, we've seen all sets have boundaries and elements, and for practical purposes in engineering, the basic rule for defining whether an element is in the system or not is an element's in the system if it contributes to the deliverable product. The system boundary is thus determined by the definition of the product.
Yeah, but perhaps we should make it clear that the word element is not used very often in the real world in industry. You're more likely to hear them called units or components, or if the component is going to be treated as a system in its own right, then it will be called something like a subsystem.
Right. But whatever they're called, what is unique about the system is the interactions between the components. To get a system, we have to recognise that it's more than just a set of components plugged together. The output from one component affects what the next component does. And the system is built up of these interactions. The connections between the components will be called interfaces, and the idea of interfaces is fundamental to the way systems actually work in practice.
Yes. So to the systems engineering, the units or the components that make up the system can be seen simply as black boxes. That is, we do not need to have any knowledge about their internal workings. There is actually a Wikipedia page explaining the theory and applications of black box concept, which is quite good.
Right, yes. In theory, the only thing we need to know about a black box is its inputs and its outputs, and how the outputs of the black box change with changes to the inputs. In the real world, we probably also want to know other interfaces like how big is it, how much will it weigh, how is it screwed down. So fundamentally, system engineering can be seen as interface control of the system's elements.
Yes, and we've already seen interfaces in my guitar setup. The guitar is connected to the amplifier using 1/4-inch jack lead. The amplifier connects to the speakers with a similar 1/4-inch jack lead, and the amplifier connects to the mains power supply with a lead that has a Euro plug on one end and a UK 3-pin mains plug on the other.
That last interface, the 3-pin mains plug, is a special case, as here the interfaces crosses over the system boundary and interfaces with the external world. Interfaces that cross the system boundary are called system interfaces, and it's through the system interfaces that the emergent properties are expressed in the outside world. The other interesting point here is that all these interfaces in the guitar setup are standards. These are another important feature of real-world systems engineering. Firstly, what is a standard? Standards are interface definitions common to many systems and that are defined and agreed prior to system development. Standards normally are controlled either by government bodies such as the British Standards Institute or by industrial agreements. The EU has 3 organisations setting standards in different fields, and globally there is the International Standards Organisation, the ISO, that sets standards globally. In addition, some industries set up organisations to manage special standards. An example is the USB interface used on almost all commercial IT products, which is controlled by the USB Implementers Forum with over 100 member companies. Similarly, Bluetooth is a standard managed by the Bluetooth Special Interest Group, and that has 35,000 member companies. These organisations are especially favoured by the IT industry because the early history in the 1960s and 1970s was of companies whose market dominance means they were effectively creating standards, but which they then manipulated for further market advantage. With standards controlled by neutral bodies, there is less scope for these sorts of games. There are several reasons for using standards. It means that you don't have to design the interface from scratch, and the components for the interface are likely to be off the shelf and which can be bought cheaply from catalogues rather than made specially. And the standard is known to work, and that reduces risk. It means that there doesn't have to be any detailed negotiation about the standard, and it is much easier to specify when there's a common understanding of the interface. The main disadvantage is that standards will never exactly match what is required, which in turn means that they've probably got more capacity than needed, and in turn that means they'll have more mass, volume and perhaps other things than a specially designed interface. Now, the use of jack plugs in the guitar setup shows that standards can be used for the interfaces within the system. And both aircraft and spacecraft have their own several standards for power and data buses, for example. But where standards really have an impact is when they are used for the system's connection to the outside world, for the system interfaces outside. This is how we interact with the outside world. And the outside world is full of standards. In many cases, the use of standards is not a matter of preference, it's a matter of absolute requirement if the system is going to be used and fulfill its real purpose in that world. Electrical goods have to have a standard plug and use the voltage on the mains that supplies them. A car has to use fuel that's available at a service station, and your phone has to be able to use Bluetooth and Wi-Fi, without which it's unable to connect with anything. Standardization makes it more likely that existing components can be fitted together into a new system, which saves costs. Properly implemented, a good standard makes it easy to introduce new equipment into the system, perhaps equipment that wasn't even thought of when the original requirements were laid down. As more systems use a particular standard, the more it becomes entrenched and difficult to change. And the downside is that standards are progressively inherited until the historical basis for that standard has long been forgotten. A good example is the 4-foot 8.5-inch railway gauge that was set by George Stephenson at the early Stockton to Darlington Railway so that he could use existing rolling stock from pony-powered coal trucks on his railway that was intended to cover the mines. This became the international standard train gauge and is now the biggest single obstacle to running high-speed trains.
This dominance of standards is not just a constraint on system design. It is standards that create markets. For example, let us look at the plug that was placed on this guitar amplifier. It only works in Britain. So the marketplace for this amplifier is the United Kingdom, and if the manufacturer wants to sell it elsewhere, they will have to change the plugs and in some cases the voltages. A problem created by countries all having different electrical power standards. The guitar itself uses a 1/4-inch jack, and every guitar uses this as an output. So if you make an electric guitar with a 1/4-inch jack, the whole world is your marketplace. And if you make an electric guitar without a 1/4-inch jack, you will not sell it anywhere. A new standard can create new products. An example from the space industry are CubeSats. In 1999, the California Polytechnic State University defined the interfaces for a 10-centimeter cube spacecraft that could be launched cheaply in a standardized dispenser. Since then, over 1,200 CubeSats have been launched, and now the majority of satellites launched each year meet this standard. It has proved a phenomenal success by any criteria. But it was not due to any technology innovation, but simply establishing a launch opportunity if you made a satellite to the standard.
We now need to introduce the key phases that a system goes through from concept through development and into operation. These are normally referred to as a system life cycle, though it's not so much a cycle as a linear progress from birth to death. There are 6 basic phases which some industries number or letter, and you will find they're called different things with different industries and places, but the underlying logic is always the same. The first 3 phases are about creating a complete proven design that is ready for production. These define the system in increasing detail using the system model. The first phase is requirements generation, which produces a system requirement specification that defines the system boundary and the system interfaces. The second phase is where the system level design team takes place, defining the elements and the interfaces which are involved in the system, producing element requirement specifications. The third phase is often called something like the design and development phase, and this is where the detailed design of all the elements takes place, including all the testing that is necessary to prove the design meeting the system requirements, eventually ending in qualification testing.
Once the design has been completed, then we can move to the next phase where we actually produce the product and where the system is manufactured and tested to show that the final product, as built, meets the requirement specification and is ready to be handed over to the customer. The process is called verification, hence the phase is often called the production and verification phase. The system can then be delivered to the customer who has the need that the system is intended to satisfy. This is called the utilization phase. But of course, nothing lasts forever. So at some point in time, the system will have to be thrown away. So the final phase is decommission, which should be the planned end of life disposal of the system.
Well, that brings our first video to a close, and hopefully you will now have an understanding of what the subject of this course is about. It's not like other forms of engineering, in that it's not about applying scientific knowledge and mathematical modelling to specific problems, but it's actually about the processes and relationships that allow engineers who work together when they have significantly different knowledge, varying skills and background. We hope that you will enjoy the course. Feedback from past students suggests that they found having a basic understanding of this subject valuable in their later careers. But I think before we leave you, Mark has a final thought to leave you with on the significance of this subject.
The development of system understanding in the mid-20th century is an extremely important moment in human history. In this lecture, we have argued that there are three pivotal moments in human development that were the thresholds to new capabilities. The first is the ability to make tools, which probably happened pre-hominid, before modern humans existed. The second is the ability to organise labour to make big but simple things. Now, we don't know when this development first occurred, but it surely was very early in human history. Then, in the mid-20th century, we reached the third development threshold, when we found a way to not only distribute the workload amongst many people, but also to share the understanding of the object by treating it as a system. Now, no one person needs to have a full understanding of everything. That understanding is distributed within a cooperating group. Now, this new ability is less than a century old, so I think we have yet to see or even understand its full potential. But it's quite exciting to think what humanity can achieve when the constraint of what a single human mind can comprehend is removed.